Hello everyone, I'm Professor Harrison and welcome back to our module on regression for finance. Today we're going to be covering the adjusted R-squared. It's a fix for a real problem with the regular R-squared, one that shows up the moment you start adding variables to a model. We're following Margot, a graduate student trying to reassemble a story her family buried. Today she's deciding whether a second variable is worth keeping in a regression or whether it's just along for the ride. She turns to the next problem in her coursework. Last time we built the R-squared, the fraction of the variation that our line explains. It's a useful number, but it has a flaw, and the flaw matters as soon as you have more than one predictor. Here's the problem. Every time you add a new variable to a regression, R-squared is going to pick that up. Or at worst, it stays the exact same. It basically never goes down. And that's true even when the new variable is total junk. Here's why. OLS is going to find some coefficient for that new variable. And almost always, that coefficient won't be exactly 0. Even a meaningless variable will line up with the leftover noise a little bit, just by chance. So OLS is going to use it to shave the residual sum of squares down just a little bit. And a smaller residual sum of squares means a higher R-squared. So R-squared ends up rewarding you for adding the variable, whether it actually helps you or not. So that makes the R-squared useless for one important job, which is comparing two models that have a different number of variables. The bigger model will basically always win on an R-squared, even if the extra variables are doing nothing. We need a version that charges a price for adding new variables, and that's what the adjusted R-squared gives us. The adjusted R-squared takes the regular R-squared and charges a penalty for each variable that you add. The penalty runs through degrees of freedom. Each observation is a piece of information, and every coefficient that you estimate uses one of those pieces up. So a model with more variables has fewer degrees of freedom left to work with. Here, n is the number of observations, and k is the number of predictors, and the penalty grows as k climbs relative to n. The effect is this. Adding a variable still pushes that explained part up, but it also costs you a degree of freedom. If the variable earns its keep, the fit improves enough to beat the penalty, and adjusted R-squared rises. But if it doesn't, then the penalty wins, and the adjusted R-squared ends up going down. So let's see this in action. Margot's looking at a small set of home sales, 11 houses in one neighborhood. She starts with one predictor, the square footage of the house, to explain the sale price. That model gives an R-squared of 0.73, so square footage explains 73% of the variation in price, which is a solid fit. Now she adds a second variable just to see what happens. She uses the house's street number. The street number is the address, something like 412 or 1180. It has nothing to do with what a house is actually worth, it's actually just pure noise. So she runs the regression with both variables in it. And sure enough, the R-squared goes up, from 0.73 to 0.74. So the regular R-squared says the bigger model is better. But we know that the street number is actually meaningless. So that little bump is exactly the false signal that we're worried about. Now let's take a look at the adjusted R-squared instead. For the first model, with one predictor in 11 houses, the penalty for degrees of freedom is pretty small. Adjusted R-squared comes out to 0.70. For the second model, we've spent an extra degree of freedom on a variable that did basically nothing, so the penalty is a little bit bigger. The adjusted R-squared ends up at 0.675, which is lower than the first model. So the two numbers disagree, and they disagree on purpose. Regular R-squared went up, and it told her to keep the street number, while the adjusted R-squared went down and told her to drop it. An adjusted R-squared is the one we should follow. The honest call is to throw the street number out and keep the simpler model. That's the whole job of the adjusted R-squared. When you're choosing between models with different numbers of variables, you compare them on an adjusted R-squared, not on a regular R-squared basis. A couple of cautions before we move on. First, the adjusted R-squared fixes the comparison problem, but it doesn't fix everything. It still says nothing about whether your model is causal or whether you left out a variable that actually matters. We'll get to that second problem, leaving out important variables later in the module. The second problem is that even if a model fits your data well, by either measure, it can still completely fail on new data that it hasn't seen. Fitting the past and predicting the future are not the same thing. Margot writes down the rule for herself. When two models have a different number of variables, R-squared alone is going to lie to her, so the adjusted R-squared is the one to trust. She's about to be comparing a lot of models against each other, so this ends up being exactly the tool that she needs. She files it away and keeps going. So that's the adjusted R-squared. The regular R-squared can only go up when you add variables, which makes it useless for comparing models of different sizes. Adjusted R-squared fixes that by charging a degree of freedom for every variable that you add. If a variable earns its keep, then the number rises. If it doesn't, then the number fails. And that's your signal to leave the variable out. It ends up being the measure to reach for whenever you're deciding how many variables a model should have.